Hello. Hi, my name is Rohit. I'm a senior software engineer here at Rokt, and I'm going to be talking about how we use Spark here, specifically for data lake ingestion. So the agenda, I'll give a little bit of a context about the data lake ingestion. We'll go into Spark structured streaming. Then we'll go into our self-service configuration, our smarter auto scaling, and then we'll finish off with Spark Connect, and then where we want to go in the future. So this is not a unique problem for tech companies at the scale that people are going right now. But the data lake ingestion, the problem here is that we have a lot of data we have to ingest. Usually they come from internal teams or partners or telemetry. They end up in Kafka, and we need to get them into our data lake. So our data lake right now is backed by Iceberg tables. So we just need a mechanism to make it reliable, but we also need to make it extensible for product teams to actually build on top. So we don't, have to do this for everyone. So for this, that middle piece right there, we are using Spark structured streaming. One of the reasons that Spark structured streaming works is our data freshness and latency SLOs are going to be, it's not a real-time system, so it's going to be minutes, not seconds. And so when we think about Spark, we think about like how do we actually, Spark processes the records in a batch. So when it comes to streaming engines, how does this actually work? So the input stream you can think about as just an unbounded table, right? The new records that you haven't processed yet, you can actually take and batch them together, and that becomes your micro batch. So that is what gets fed into Spark, and that's what it's going to, you're going to do your business logic on. So as we go on, we can see some of the pseudocode here on what we're doing. So you can see that we're going to have some options on triggers, checkpoint locations, and then our business logic. So for Spark structured streaming, what we have is a trigger. How often do we actually invoke this? What's the actual time interval that we're doing? And then we have the checkpoint location. So when it comes to Spark structured streaming, you have the micro batch, but how do you actually know where to start, right? Or where to continue when the Spark application actually dies. So the way that it does it is it's going to, at the very beginning, write to a write-ahead log for which batch it's going to start. Once it processes, it's going to write to a commit log. So if that Spark application dies, comes back up, it's going to read the last checkpoint location and then figure out where to start from. In our case, we're using S3 to store these checkpoints. And then our business logic here is going to be merging into Iceberg. So our data lake ingestion is deliberately simple. We're relying a lot on the Iceberg tables in order to do, deduplication. So we store no state in our Spark structured streaming. And that, again, is deliberate. This is very simple when it comes to the code and managing. One of the cons is once we actually start doing deduplication, if you start inserting, for instance, if you have an Iceberg table that's partitioned by day, for example, and you get a whole bunch of records that are a year old, what you're going to have to do is you're going to have to, that batch insertion into Iceberg is going to take a bit, right? Because now it has to go through each partition. So that's, one of the challenges that you face with something like this. You could get a little bit more creative and have a sort of like deduplication store, but that's something else that you have to manage and keep track of. So great, that is our code, but now I am a product team, right? I'm a product team and I have some records in Kafka. I need to get them into the data lake. So how do I do that without, becoming an expert in Spark? So we expose a YAML configuration. And the idea here is that if you're a product team and you actually want to get stuff into the data lake, it's 20 lines of YAML instead of, writing your own Spark code. So here, you can see the highlights here are you're going to specify your source topics. You're going to specify your partitioning scheme, ingestion mode, and the batch trigger interval. So in our specific case, if you look at the top, you see the stream groups. Each stream group is going to match to a specific Spark application that we're running on Kubernetes. And each Spark application is running multiple streaming queries. So at this point right now, we are running hundreds of streaming queries across dozens of Spark apps. And one thing that we have noticed in this age of AI is that there's a lot more demand for product teams to actually start ingesting into our data lake. The reason, or one of the reasons that we've seen is that with AI, code generation is now super fast, right? But you still have to verify whether that code actually works. So at a scale, at the scale of a company like Rokt, right? There's a lot of data that how do we actually know whether the code is working? So a lot of teams are actually taking, they're rewriting their system or they have a new system, a new architecture, and they're streaming shadow data into another data lake table. And then the way that to do verification is actually joining on shadow and prod to see what the data differences are, what data is missing. And that's a good way for teams to actually figure out whether their code is working or not. So great. That's all great. I'm a product team. I can get data into the data lake and everyone's happy until the bill shows up. And hundreds of these streaming queries, right? We need a way as a platform team to actually start consolidating some of this cost. So Spark has an internal, it's called dynamic allocation. But the way that the idea of this is that it's going to try to optimize your executor count. So you have drivers, you have executors, and executors are the knobs that you're turning to actually get more compute, right? So the way that dynamic allocation works is that you start a Spark app and there's a queue of pending tasks, right? So it's going to look at that pending task queue, and from that number, it's going to try to get the number of executors that it should be, right? So this breaks a little bit when it comes to Spark structured streaming, and the reason is because the source is now essentially different, right? We're looking at Kafka, right, instead of a specific batch from Spark, right? So what you really want to look at is you want to look at the Kafka consumer lag, you want to look at the trend of the lag, and you want to look at the batch efficiency specifically, right? The dynamic allocation, it only has access to the things that Spark can see, which is this pending task count. But for us, we want to be a little bit smarter about how we actually scale. So what we did is we created a custom scaling server. And this is a very high level architecture. But again, the goal here is how do we want to keep our latency reasonable, but we want to not break the bank with the cost. So the idea here is that our Spark driver is going to be a scaling client. It's going to call the scaling server. We wrote a custom Spark plugin. Every minute, it's going to send an HTTP request to our scaling server. The scaling server has a bunch of logic, but one of the things that it does is it calls into our AI model with all the context that it has. And then at the end, it's going to give back an executor count to the Spark driver. The Spark driver is then going to talk to the Kubernetes cluster manager to actually provision those pods and those executors. So the idea is this is fail open, but the idea here is that the scaling server itself can have a lot more context on what is happening. So it can look at the metrics from Kafka, can call the AI model, and it can return that back. The AI model that we're using is Haiku 4.5, and the reason I call that out is because it's the cheapest one. So in specifically the scaling server, our scaling logic, it's a little bit involved, but at the end of the day, we get some input signals from Kafka. We are building a prompt that we are sending to the LLM. The LLM is going to output strict JSON with a specific action, the target executors, the confidence, and the reasoning. So the primary thing that we are going to target is specifically the batch efficiency. And what that means is for every Spark structured streaming query, it has a trigger. So that time interval, for instance, if you set it as 10 minutes, for example, ideally we want that batch to complete within 10 minutes. If it's too fast, that means you are probably wasting executors. If it's too slow, then that means you probably need to scale out. You need a little bit more compute. The other thing that we do is we're actually grading the LLM outputs. So every time we call into the LLM and it gives some sort of decision, what we're doing is 5 minutes later, we're dispatching a task for grading the LLM. So what it's doing is it's looking for the past 5 minutes, and it's going to classify whether this was a good decision, bad decision, or an acceptable decision based on how the lag is trending. So for example, if the lag is going up and LLM decides to scale down, the decision after 5 minutes, the lag continues to go up, is going to be a bad decision. What we do is we're going to take that, we're going to feed that back into the prompt so the LLM can have more context on what decisions it has made in the past. After that, we have some sort of deterministic rules after that LLM call. So the LLM is going to return its recommendation for the number of executors. After that, we're going to do some validation. So system bounds, we can't go below the min executor count and above the max executor count. We have the concept of cooldowns. So, scaling up in general should be pretty fast, but when you want to scale down, you want to cool it down. You don't want to scale down too fast because you start executor thrashing, and usually that doesn't help with cost and it doesn't help with the workload. And the other thing is step limits. So if you're at 10 executors right now and the LLM suggests 1,000, you probably don't want to scale out to 1,000 right away. This actually bounds the number that you're scaling out, and then you can actually see the system evolve over time. So you can see whether that's heading in the right direction or not. The other thing is that we actually do, which is pretty Spark specific, is vetoing scale down decisions. So sometimes the LLM is going to want to scale down, but in certain situations in Spark, you don't want to scale down because that is detrimental to your streaming query. So for example, if you do a shuffle, what's going to happen is those executors are going to write shuffle blocks to their local disk. If you scale down and you kill those executors, what's going to happen is that stage is going to have to restart. And that is essentially, you're trying to save money, but you're going to have to go back and restart specifically that stage. So specifically, when the AI goes back to the driver is looking at which executors have shuffle blocks on them. If it's a scale down decision, it's going to veto that decision. There is one small edge case there, though. Shuffle blocks that restart the stages, we want to veto. However, there are shuffle blocks that are from cached data frames, and ones, cached data frames, and ones that can be recomputed. Those specifically, you do not want to veto because, for instance, if someone actually caches a data frame and the LLM wants to scale down, if you always veto that decision, you're never going to end up scaling down. That was a tricky edge case that was there. But specifically stages or shuffle blocks that are going to recompute stages, you do want to veto. I want to take like a minute to talk about Spark Connect specifically for two reasons. One reason is that we rolled this out and there was a lot of demand across the company for using Spark Connect. And second is I want to talk a little bit about the architecture because it's pretty cool in what it does, and it kind of aligns with where we want to go into the future with. So Spark Connect, the idea is that there is a boundary between the client and the server. So you as a client don't actually need to be a Spark engine to run Spark code, right? So what the client is doing is it's writing the Spark code. It's going to take that Spark code and create an unresolved logical plan. It's going to serialize that to protobuf and send it over gRPC to the server. The server is actually a driver. So it's listening for that gRPC request. It's parsing that plan, and then it's going to turn that into a physical plan and then run it. And the results are shipped back to the client via Apache Arrow batches. So the idea here is that the clients, right, don't actually, they can be in any language, they can be different versions than the server. There's a strict boundary between what it is. And this is pretty interesting in where we want to go into the future, because if you think about it, right, if the client is the one that's writing the plan, right, the server actually takes that plan and just executes it. So stepping back here, what we want to be as a platform team, in general, all platform teams, what we want to strive to do is we want to try to abstract away everything but the business logic for product teams. So if you actually take a look back at that YAML configuration that we had, you can ask yourself, like as a product team, why do I care about which stream group or which Spark app my business logic is running on? It doesn't really matter, right? What we want as a product team is, here's my logic, right? I don't care where you execute it. I don't care what you do with it. I'm just going to give you my SLO, and I want you to get it done within that time. So the idea here is that in the future, what we'd like to have is some sort of data lake control plane where people are going to have their specific configs. And what we are going to do is we're going to be a little bit smarter about where we are actually running those. So our, at the very bottom, you can see like the fact that all we need is some Spark runtimes, right? That we can actually take those streaming queries and just run where we need to. We can do the same for Spark Connect with a Spark Connect gateway. And one specific example that this solves is, imagine a product team starts, has a config that they want to run. AI generated code, no one really wants to test it. They haven't tested it. We don't have the time to test it. So how do we know whether it works? Right now, what happens is they drop it in a stream group. Maybe that stream group is important, and maybe it just brings down that stream group, and there's nothing there. Then someone gets paged. We got to go in. We got to roll it back. We got to fix it. In this case, it would be pretty trivial to add a rule where any new config, any new streaming application that someone wants, goes through this router brain. The router brain detects that this is a new stream group, so it's going to put it on its own Spark application. And when it does that, if it fails, it doesn't matter, right? It's not going to affect anyone. It's not going to do anything. We can page the owning team so that they can go in and fix it. The other thing that we can do is, for any new configs, any new Spark applications, they can run on their own environment. They can run for a couple hours, maybe a couple of days. We can get some more signal on how it's doing. And then from that signal, we can actually consolidate with the other Spark runtimes. So that way we can get kind of a generalized version of our autoscaler and just a consolidated view of what's going on, where the actual decisioning lives in the control plane instead of the configuration that is client provided. But yeah, this is where we want to go. And yeah, I am fortunate to be able to present this, but there was a lot of work done by a lot of people. So yeah, that was it. Any questions? Yeah.
Yeah, thank you. Yes, I will repeat the question. How do you solve the problem of the window optimization itself of this structured streaming? For example, how big should the micro batch size be? How fast should like the TTL be in order to write the data to the table? And does DataFlint offer such ability to do like window optimization on Spark structure streaming?
So I think maybe I'll let DataFlint folks answer the second part, but for now it's a little bit naive in the sense that we have configuration on the max offsets that we're pulling, and from the YAML, the trigger is client provided right now. So that's something that we want to change in the future. I think we default to around 10 minutes for the triggering, but yeah, in the future, what we'd like to have is let's set a trigger and then let's figure out, how long the batch is taking. And in the future, it would be nice to actually figure out how many executors we're running with to actually provide some sort of cost, right? So then at the end of the day, all the producer team cares about is what is the cost and how does that differ if their SLO increases or decreases? And then we can try to figure out what the actual config is.
Yeah, I'll just refer for like the DataFlint team. So there is multiple ways to do Spark streaming autoscaling. There is no like true way. One of the ways we know to help is that there is a set of configuration for which streams you can control. For example, the max row per window, let's say 100,000 or so on. Like you can set the number to maximize the number of rows, minimize the lag while keeping memory under check. There is a new feature in Spark 0.4 called the rows per partition, where you can decide, like, let's say 100,000 rows is one partition, and then you can control the number of partitions. This way, auto-scaling could look at the pending task if you have like less executor and like increase it to support the lag. In the end, like trigger time is still very useful. Like it helps like managing SLA. If, like the question again, what you're optimizing: cost, delay, SLA. It is a complex problem. We know to like give AI all the context it can from production to make decisions. We prefer to do that like versus the amazing Rokt approach that they're actually making decisions in real time with AI. The more naive or safer approach is to set a number of configuration depends on the production usage and like add it to your code, and then it's like it's not a production like issues that you need to monitor all the time. It's just like a set of configuration on your Spark session. So that's from our end.
Yes.
I don't need to like it too, and I'm logging out. Can you describe in more detail how the shadow data process works? You had mentioned before generating shadow data and joining that to production data to test downstream workflows.
Yeah, for sure. So for instance, like a product team wants a new architecture, I don't know, a new technology or something like that. And you can think about maybe like their application like consumes from a Kafka topic or something. They're doing something and then they're outputting to another Kafka topic. So with AI generated code, it's like, how do you know whether that works? So they write their code, they set up as a new deployment. Maybe it's a new Kafka consumer group that they consume from. They run their new architecture and then they output to another Kafka topic. So that other Kafka topic, it doesn't actually do anything, but their data is still there. So what they're doing is they're outputting both streams into the data lake. And the idea is that if you're doing some sort of refactoring or new architecture, the data should be the same, right? Maybe you're doing a speed up, maybe you're doing, I don't know, something else. So it's just a process, like a way for verification just on big data. So at that point, if you output the same data, then you can actually run, like using Spark Connect, you can run queries that match that data and just verify whether your new system is doing the same thing as your old system. Yes.
Yeah, I have a question. Thank you. So I have a question on the LLM layer. So how you guys are using tier 1 to tier 4 to reason via LLM? I mean, are you using deterministic approach to the LLM for reasoning?
Our temperature setting on the LLM is very low, so creativity is very low.
Okay.
Near deterministic, yeah.
Thank you.
Thank you. I just have one, like when you have implemented the AI for the executors and all. So do you have any metric which you have targeted? If you could share some numbers, like it's solved 20% or 30%, whatever it is. So what metrics are you targeting when you have implemented this AI execution plan?
Yeah, so when we rolled this out across the entire fleet, I think there was like a 7 to 8% cost reduction just from the number of executor scaling. I'm sure tuning it more, we can probably bump that number up. There were certain stream groups that were that did really well when it came to the executor scaling. Yeah.
Thank you.
Yes. Yep. Yes, we tried that, and I believe there were some bugs that we ran into where there was like a memory leak or something like that, so we had to shut it off. I don't think we had time to dive deep, but yes, I think that's something that we tried. Essentially, graceful decommission is taking those shuffle blocks and then it sends them to other executors. I don't remember what the problem was, but I remember there was a problem. Yes. Unfortunately, there were some bugs that we ran into. So one was iceberg side is sometimes so we were using glue, and sometimes when there is a rate limit issue with glue, it thinks that it has not committed, even though it has, and then it goes and deletes the old snapshot, and then the table is now fucked up a little because it doesn't have the old snapshot. So unfortunately, you got to go and manually fix that, point it to the last snapshot. We have run into very interesting issues when trying to deduplicate within a batch and write to iceberg. Very interesting issues that we just need some time to dive into it. Yeah.
On my previous question.
Yeah.
So, like, those deterministic layer, do you use it to reduce noise coming from the LLM?
Yes, that's the main purpose, because I still think that trusting the LLM fully is probably not the best move, specifically for like cooldown. For instance, if the LLM wants to, like you're at 10 executors and the LLM says, hey, let's go to 1,000, you probably don't want to go to 1,000.
Right.
So it's probably just like smoothing it out. And then especially when you want to scale down, scaling down should probably be a smoother experience than scaling out. So yeah.
Thank you.
I want to ask a question regarding the table format that you have chosen. I understand that you are using very often structure streaming, right? Real-time data, almost real-time data. Why are you using then iceberg tables and not, for example, data tables or Apache Avro format?
That's a question that probably predates me, unfortunately. Yeah.
Last question.
Thank you. It was an interesting presentation. I just have a pretty straight up question to ask is, what's the size of your Kafka cluster and how many topics do you run on that, or your platform team has the Kafka team to handle that? And the other question is, in terms of scaling, what is the max in terms of messages per second that you flow into the Kafka cluster? Does that make?
Yeah, that's a good question. I don't want to say anything wrong. Maybe someone else here at Rokt, maybe Bruno has has an answer. We run probably hundreds of topics. Each of them are probably like maybe 16 to 50 partitions or so. Ingress, maybe like a couple of gigabytes a second peak, yeah, right? Yeah.
Amazing. Thanks you, Rohit.